We are settling in, and I guess that we can start. I'll just check how many people are already here online. Okay, so I think we can start. Welcome to everybody online and in presence. So for the second day of the workshop, Anthony and Silvio will show us the hands-on exercise.
Exactly.
Deep learning.
Yes. Right. Well, thank you again for inviting us, and for that second day. Thank you for the survivors and to the people that are excited to code. Today we're going to have a hands-on exercise. We're going to work mostly on Jupyter Notebook and Python, and we're going to go through the dataset of FLOGA and take a use case of how we can extract some information out of these satellite images. We're going to explore the data, we're going to extract some indexes, we're going to train some machine learning algorithms as well. We're going to show how to evaluate different performances of algorithm. We're going to train some deep learning algorithms, and we're going to have some hands-on on GeoSam. That's actually the slide of the outlines. First, we're going to have like some data processing to understand like how FLOGA work. Then we're going to play with indexes. Then we're going to play with machine learning algorithms, analyze performances, and how to evaluate scores of how good is an algorithm. Then we're going to work deep dive into deep learning, and finally have some hands-on on GeoSam, and everything is based on the FLOGA dataset I presented yesterday, which are fires or burnt area in Greece. So for that, I have actually prepared a development kit for everyone. So we're going to use Google Colab, and we're going to use Google Drive to basically go over the different materials. Maybe with like some raise of hands in the room at least, how many people already are familiar with Python? Good, perfect. Okay, I was afraid of that because we're going to use extensively Python. Goes through Jupyter Notebook. So I will take actually that link here, and I'll share that also in the WebEx. Oh, can you do it? Perfect.
No, if you can do it.
I can do it.
The chat.
And for people in the room, you can also scan that QR code. I think this QR code is in the middle of the TV, so I don't know if I put it on the side, maybe it's a bit better. Here you go. And we are going together through that folder. Is it working actually?
I shared it on the chat.
All right. So this Google Drive link here is a dev kit that I've prepared for everyone to play around. It contains data, notebooks, including the solutions actually, and some pre-trained weights of large-scale models that have been trained already on FLOGA, and some logs of training that we're going to analyze together. Giving a bit of time for everyone to access that. Oh, you can actually like have a live demo with me so I can see what it's actually doing. So the first thing that I would ask everyone to do, if you have in the same page that I'm currently I am currently here, there is like one operation that you need to do, which is creating a shortcut of this development kit to your own Google Drive. So if you're actually on a laptop, it's better to use a laptop. I would just ask you to click here and then go to Organize, add a shortcut, ajouter un raccourci in French, and add that shortcut into your main folder in Google Drive. Or it won't take any storage in your Google Drive. So if you go to particular, you have something called Drive. You can just wait a few minutes just to make sure.
Maybe
Yeah, interesting.
if you can repeat.
Yeah, so I will repeat
that
that
step.
again.
Just
Okay.
so on the chat for those who are just. Okay.
Chat. We're going to go slowly because that's the number one step. So. But once you have the development kit, basically, what do we have available in that development kit? Basically, the files of the dataset FLOGA. We have the weights of the models that have been pre-trained already. The notebook we're going to work on, a Jupyter notebook, encoded in Python, and some logs from a library called Lightning, where we can analyze and show like how a training take place. The reason why we provide also the logs is because when we actually train deep learning models, sometimes it takes hours to train, and we train the model already of one of the models like DeepStudy and BAM-CD. We already have the weights trained. It took like a couple of hours to train it well. So we can just analyze the logs and load those weights around it. We're still going to train for a few epochs to give you an insight of how training actually works, how the data cleaning and data preparation looks like. Good. So again, from that link, once you arrive to that link that I just shared on the Slack, on the WebEx and here, you just click on the folder CV4EO dev kit. And there is an option for organizing that folder, and you just need to create a shortcut. And that shortcut needs to be in your main folder on Google Drive. Why is that? Because when we're going to play with the Google Colab are instances of Jupyter Notebook hosted online. They basically have some compute power that is available for researchers to play around with a few lines of code of Python. And we're going to mount your drive, the Google Drive, to the Google Colab. So you will have access to all your files that is currently in your Google Drive. And by adding a shortcut of that dev kit to your Google Drive, you would have access to the data of FLOGA and the different notebooks. So adding a shortcut in all location, my drive, just click the button add here, and you will see it in your main drive. If you go to the left here, there will be a folder called CV4EO dev kit, which is a shortcut for that. I have two right now, so just one of them, opening the other one. And basically, you have access to these files.
Are we going to need QGIS as well?
We might use QGIS because we're also going to output some of the data of FLOGA. FLOGA is stored in a shared format that is convenient for data sharing called H5, which is very condensed zip versions of the different satellite images. And we're going to create GeoTIFF images of that. So at some points when we're actually going to extract indexes or masks, we're going to save them in GeoTIFF, and we could actually open them in QGIS. So I'm only familiar with QGIS, but if you have any other GIS software that you are familiar with, feel free to use your own software.
And it's optional, right?
And it's optional, of course, yeah. We don't need to use QGIS, just to show you that we can actually extract GeoTIFF images. Great. Good. So I guess we all have these dev kits ready for us. So we're gonna go, so let's explore a bit these folders. The first one is just a cache that has been created automatically, so it won't take time. So the dataset of FLOGA is there's different versions of it. There's 3 versions with for Sentinel-2 a resolution of 60 meters, 20 meters, and 10 meters. But I haven't included the 10 meters here. It's like very large files, and we're only gonna use actually the 60 meters for the sake of that examples. Basically contains one file in the format H5 for every single year, 2012, 2017, 2018, 2019, 2020, and 2021, that we're going to explore. And each of them are around gigabytes of data. Then on top of the data set, we have some model that has been trained so far. We have a random forest classifier that has been trained. And we have some algorithms, DeepLab v3, 2 versions of ANSYD that we have created. We have already trained them for you, so you can later on just load the weights and play around with them to basically run some inference, for instance. And then we have the different notebooks. We have 6 notebooks today. They are from part 1 to part 6, and it corresponds to the 6 sections that I presented in the slide before. So basically the hands-on work beyond first data processing, second playing with indexes, machine learning, performances, deep learning, and geoscience. In terms of timeline, I do believe that the first 4 sessions will be quite easy for most of you. So maybe you can try to reach for the first 2 hours until the section number 4 on performances. And then we're going to spend the last 2 hours on deep learning and geoscience. This is how I see the time can actually go. So if we start with the first file, if you just open it with Google Collaboratory, that's the first part that you can see here. So that's a Jupyter notebook. Maybe raise of hands, who is familiar with the Jupyter notebook? Perfect. It's okay. Amazing. So, if there is any issue online or how to access the data, please let us know. Here, could you follow right now?
Yeah, not solutions and part 1.
Okay. So a few minutes.
Shortcut.
To the right.
Great. Okay. So Google Colab is a Jupyter notebook online, as you can see here in that here. Jupyter notebook is basically a bunch of cells that are either text or a piece of code that you can run one step at a time. Google Colab is a way to run Jupyter notebooks. So this format IPYNB, which means Interactive Python Notebook, or something like this. You can run them directly on Google Cloud by connecting your Google Colab, your Jupyter notebook, to Google Compute Power. So the first step would be to connect your Jupyter notebook to a runtime by clicking on the Connect button on top right. And basically what it's going to do is basically going to allocate an instance on the cloud to basically run your Jupyter notebook. Here in particular, I'm connected to Python 3 Google Compute Engine backend with 12.67 gigabytes of RAM, and I have a disk that I can use of up to 107 gigabytes of data. If you click here, you can also have different information about the different resources that you can use. You can also change the type of instances. If you want to have some GPUs for training, for instance, you can change the runtime type, and you can have access to NVIDIA T4 GPUs online, or TPU, which is a specific tensor processing unit that is built by Google, that is also suitable for deep learning training, for instance. But since in the beginning we don't need any GPUs, we're going to still use the hardware accelerator, which is just a CPU, because we're in the first sections we're actually going to use fully CPU. We don't need the GPU because we're not training any model. All right. That being said, you should be at the level where the Jupyter notebook is connected. So you have connected, and the different shortcut for you to know if you want to process one of the cells. So here you have one cell, here you have one cell, here you have one cell. Is just to press Shift and Enter, and basically that's going to go step by step and compute one cell after the other. So the first part basically explained a bit what's that workshop about, and today we're going to explore the FLOGA dataset. There is some resources here, both the paper of FLOGA, if you're interested in reading more about the details of that specific paper, the code provided by FLOGA, and the model that they have developed called BAM-CD, and the datasets, access to the dataset itself as well, which is hosted on Dropbox. And we're going to use Google Colab for free GPU resource access. I think you are limited to maybe GPUs like maybe 5 hours per day, which is more than enough for today. If you are using it more extensively, because it's based on Google compute engine, you might actually have to go to a pro account. So it's very useful for a workshop like this, but in the future, if you want to train at large scale, you can actually export that Jupyter notebook and run it on your workstation as well. That's working as well. So the first step that I'm going to run is that first cell. I'm going to basically create the environment in my Jupyter notebook. And as you can see, first of all, on the left here, you have some buttons and you have a folder here. This is the access of the storage that you have access to from your Jupyter notebook. So right now, I have only access to a folder called sample data that might contain a few informations, and this is typically very small data sets that are used for deep learning. You can recognize like the MNIST data set that I mentioned, the numbers that I was showing you yesterday. This is access to download them. And another one is basically, these are 2 data sets of California housing, very used in machine learning exercise to train some algorithm to estimate the cost of housing in California. But of course, this is not our data. What we're looking for our data is currently in our Google Drive. So if we run the first cell, by either playing the play here or Shift Enter, we're actually going to connect our Google Drive. The first step is basically to click on Connect to Google Drive here. You will be redirected to a page where you will have to select your Google account and give access to Google Drive to your Google. To give access to Google Colab to your Google Drive. And once you granted that access, it will basically mount your Google Drive, your storage, in a path that is defined by this path. So /content/drive. So once that is mounted, we can refresh the list of files that you have access here. And if you open that drive, that folder called Drive in My Drive, you might have access to all of your files in Google Drive, but the one that I want you to look at is the CV for Earth Observation Dev Kit, which are basically the different files that I was presenting to you before on my Google Drive, which is basically this folder here. Don't look at this dot something, it's a hidden file actually that does not appear. It's a cache. So now we actually have access to the dataset. You can see the dataset here, for instance, 60 meter. The files are actually available here, and we can actually process them. And you can also have access to some models and so on and so forth. So the next step is to install some libraries. Is anyone actually on page with that? Should we? Is it like too slow, too fast? I'm happy to have any interaction with you just to understand if I'm too slow, too detailed. This is.
Well, just one thing about those images, I don't see them here.
You don't see them here? Okay.
No, I mean, I'm using Windows machine, but...
Oh, that shouldn't be a problem. Because
yeah, so here
If you're running like this, you can click on the
just the folder. Okay.
there,
Yeah.
My Drive,
I drive, yeah. Okay.
My Drive and then CD folder.
Thanks.
Great. Feel free to interrupt me at any point, write on the chat.
And
So
I'm
like
here to go around as well and help.
Drive, my drive, agree, show the rest.
It's like with live demo, there's always bugs and issues everywhere, so I'm pretty sure we're gonna run into so many issues, but we're here to try to help you figuring out how that works.
No comments.
Okay, that's great.
That's where you have to do the short.
Computer.
Next steps is basically to install some Python library, and in particular, we're gonna use this Python library, which are H5PY, HDF5 plugin, HDF5 widget, which is basically tools and library that handles H5 files with the storage of how that document that set was shared. Matplotlib, which is a library to plot images or graph in general. IP widget is a way to interact with interactive Python widgets in your Google Colab or Jupyter Notebook. And Raster.io, that you might be familiar with, is a tool to read or write or sometimes display, I think, GeoTIFF images, for instance. So we're going to run that line of code as well by either clicking play or shift enter. And that's basically going to install a few libraries. As you can see, basically, when something is running, it's basically shown here, like it has run in 10 seconds in that specific case. When it's running, you can see it's actually moving. So you can know what processing is currently done on your computer. So here I then define some path that will be useful for to access our data. So the dev kit for all of our Jupyter Notebook will be basically in the content drive, my drive, CV4EO dev kit, because we have created a shortcut of the dev kit in that specific folders, and everyone should have the same folder. Then the dataset, the folder for the dataset is basically dataset FLOGA on top of the dev kit. The dataset path is basically the one we're going to use to play with on in this first hands-on. Will be the Sentinel 260 meters, as well with the MODIS 500 meters. And in particular, we're going to use the FLOGA dataset 2017. Yeah, this is the one. So this is the files, the H5 files, and it's available in that variable. And I'm also going to create an output folder. That output folder is something that you will own. It's not something that is just a shortcut that we have mounted in your drive. I will actually create, each of you, by running this line of code, will create the folder for all the output that's going to be generated. So here we're going to store all of our images that we are reading, maybe the GeoTIFF format, so we can actually read it with QGIS or other tools that you are familiar with. So when running that, so I'm just like setting some variable. That's it. And you should have now below the CV4EO dev kit something called CV4EO output. That right now we should only have the part one because we only have played with the part one. And here we are gonna store some GeoTIFF files that you don't have yet, but at the end of that Jupyter Notebook you actually have. So, all right. If that is set, now we can actually start to deep dive into the FLOGA dataset. Everything is good? All right, maybe I will try to be a bit faster because I think too many details. So in these details, so we want to understand first the structure of the FLOGA dataset stored in HDF5 format. And we want to learn how to load and inspect the pre- and post-fire Sentinel-2 satellite images. We want to visualize the data, including the spectral bands and the binary labels for the burnt area. So we need to make sure that we have the FLOGA dataset downloaded and accessible, which is already the case here. And we have mounted our Google Drive to save the output. So the first things that we're going to do is that we are importing the H5 file in that line of code, and we create a viewer for the with the HDF5 widget for my dataset. And I'm going to display that dataset. So here what I'm doing is that I'm loading the dataset that is stored in that variable. It's actually Google Colab is quite intelligent and tells me that the value is like content, drive, my drive, CV4EO, devkit, dataset, FLOGA, and so on and so forth. And when I'm running that, it's actually reading that path and displaying it. It might take some time. It's computing. for you? For me, still loading. Great.
Works.
It works for you too? Perfect. So here we can actually explore what the HDF5 file look like. And basically, it's kind of a very compressed dictionary in Python that contains all the information and display for you all the information. And if you click on the 2017, you can see that there is many entry inputs that have some indexes. This is how it has been stored in particular. And each of these indexes represent one satellite images that contains many different informations. The 7 actually information I showed you yesterday, which corresponds to those 7 information. So we have the pre-Sentinel, the image of the Sentinel fires, the Sentinel-2 image from post fires. Same with MODIS, post and pre-fires. The label of the fire that we can see quite easily here. The CLC and the water mask. So if we look at our structure here as well, we can notice that we have information about the CLC, the label, the mod 500 cloud post. We also have a cloud information of post images, post fires, pre-fire. We have the mod 500 post fire, pre-fire. We have the mask for the sea, and we have Sentinel-2 cloud post fires, the Sentinel-2 cloud pre-fires, and finally the Sentinel-2 post and pre-fire images. When you click in on those things, you actually have some information about the shape of this data. So what does the shape mean? You remember yesterday I told you about matrices and tensors. Deep learning is all about managing tensors. Tensors are higher dimensional matrices. So if I look at the Sentinel 260 cloud post, just like the post, do you have any idea of why the shapes is actually 11, 1626, and 2040? I guess it's quite obvious that the first 11 dimensions are the 11 bands that are contained in the Sentinel-2 image, and the rest, the other dimensions, are basically corresponds to the dimension of the images themselves. All this information are stored in int32, so an integer in 32 bits, and it contains the information of all those 11 bands. So imagine that you have a 3D tensors of 11 times 1626 and 2044. And those are attributes also. So this is what the information that is stored in terms of data. We also have the CLC. The CLC is actually the label of the land usage class, the land use classes, and there is a shape of 1, same resolution of the image, and it's an integer, since it's just the labels that basically 1 might mean water, 2 might mean something else, and 3 is the different classes, and so on and so forth. And the label finally is also same shape of dimension 1 and the resolution of the image, which tells us the information of where the fire has happened. And if you look at the attributes for that specific entry, you can also see some extra information of when that image come from, the MODIS files it come from, the Sentinel-2 image it come from, the pre-image date, so that's post-image date and that's pre-image date, so before the fires and after the fire. So that's basically what a dataset looks like. That has been curated data from this Greek team that has put together all the information that we need in a clean fashion. So as you can see, we basically have a very clean way of, for a specific image, you have the labels, and now we can actually use these informations to train neural networks. We can only focus now on the expertise, which is like extracting the information out of that, or train a neural network to train a deep learning approach to extract the information you're looking for, without necessarily having all the knowledge of where those images come from, for instance. We can still like retrieve them back, but now we can actually focus on analyzing those images.
So the label, so where the fire is located, how was that triggered? I mean, was it done manually or was it done
manually? Yes. So typically, when you create a data set, you want to create data and informations, and annotations to the community, and these are usually manually annotated. And when you release the datasets, as we mentioned yesterday, there's always like human errors. And that creating dataset is somehow quite tricky because you want to reduce as much as possible those errors. So it's not something that you do in a few hours. It's something that actually is a lengthy process when you have quality assurance, maybe multiple annotators that annotate the same area, verify, and the more clean the data are, the more faithfully representing that fire that is, the better. So those are experts in their area, and they have labeled those data. So I don't know how they did that in particular, but I guess they look at the images and they decided where's the fire by hand, by taking a lot of time in drawing the boundaries of those fires.
Yeah, so are there best practices to instruct and to do a labeling exercise, let's say? So like many people, number of points to label and so on.
That's up to the expert in the domain. So the more accurate, the better, of course, because the guidelines could come directly. Typically, I would say like this. This is basically the output that you expect your algorithms to extract. If you give them noisy labels, that is not accurate enough in terms of polygons, number of points you actually use to draw the contour of the fire, for instance, you can't expect the algorithm to be better than that. So we're going to use these labels to actually compare any output of any predictions that our algorithm will do to that as a ground truth. So we will consider that as being 100% accurate. And when we're drawing some performances, we are going to take those labels as a reference, and whatever we're going to predict, if it's not matching those expected output, those expected labels, we will consider that as erroneous, like not performing well. So this is an extremely critical aspect that highly curated data are usually needed in order to have good evaluation, good benchmarking. Because imagine if I have some boundaries or images or presentations that are not precise enough, then if I create an algorithm that is extremely precise, I might actually give wrong performances or like a bad score to my algorithms just because I'm more precise than the labels. So I want the labels to be as precise as possible. I don't know if that answers your question.
Yeah.
Can I ask, are there any standards also, guidelines about where you're recording the label, like the pre-image, post-image, what you can see in the attributes?
You mean standard in terms of?
Kind of metadata attributes that you record on the label.
It depends on what you want to work on. So for instance, this FLOGA dataset is used in a model that's called BAM-CD that actually takes the pre and the post fire. So in that specific case, they wanted to use, they had access to this as an input, and they have an algorithm that actually take those two inputs to create the outputs of where the fire is. So in that specific cases, they needed big data. But if you want to build a dataset that only take into consideration the post fire, for instance, and you just want to, or just like, you don't need like the before and after specific event, you can also create your own dataset that basically just covers the data that you have available. Usually the process is mostly, what do I want to achieve? In that case, localizing fire. That's what's the output I'm expected, and what's the input I have at my disposal. And the more input I actually give to my models, the better that is. So if, for instance, if I only have access to RGB images, for instance, I will basically create a dataset with just RGB images. But is that enough to create the fire, to have the burn area located? Maybe not. So maybe I would actually increase like more data with like the 11th length of Sentinel 2, or more information, maybe higher resolution. Here, for instance, I'm only using the 60-meter Sentinel 2, but there's also the 10 meters that is available. I'm going to use the 60 meters because for me it's enough, but maybe for other applications, you might want to actually have a finer resolution of the satellite images. So it depends a lot on what you want to perform. And, usually that's where the domain expertise actually comes into place. some experts in artificial intelligence don't know necessarily what type of input data is useful to localize the burned area, or if you want to understand like the vegetations of some places. And this is where the domain expertise and basically expert that identify that that wavelength is actually highly correlated with the fact that there is high vegetations in that area. That's actually the type of input that you would like to feed your artificial intelligence networks to learn from.
We also have a question from Quentin, who says, personally, I've had a better success with a little error in the dataset for generalization. Any feedback on that? However, same opinion as yours regarding validation. The more accurate the labeling, the more representative the metrics. Have you had experience with that? Personally, I've not seen like errors in the training data that helped improve the generalization. But I'd be happy to have a look at some experiments that you have on your side regarding that. I don't know if you have seen that already.
I haven't seen that particularly. It depends what type of error we are talking about. If it's realistic errors, then that's good. It could be considered as data augmentation somehow. But no, usually the more accurate, the better. It's like when you want to learn something from school, you would prefer your professor to tell you exactly the truth and not something a bit random with noise. But thank you for the question. Happy to look into your data content. Okay, so next step, reading from this HDF5. Here we have a piece of code, a class that I've already, it's already written for you. That's taking into consideration raster IO to read those data. It's a class in Python that has a builder that can read some file path specifying the year and the event ID. So I forgot to mention that this is the year of that specific file, and then every single numbers here is called an event ID. And it contains multiple information. So if I want to read and process one of these files, I can specify which year I'm considering and the event ID, and that will basically run the H5 Python line of code that will look for that specific event data in my file and load the event data for that specific, the satellite images for that specific event data. And here in particular, we are loading the Sentinel-2 pre-fires, Sentinel-2 post-fires, and the label. Then it calculates some metadata. So if we want to print some statistics, we can actually print some statistics. And when you run the get data, it actually returns the pre and post fire images, the labels, sometimes the band names, and the metadata itself. So that's something that's very already provided to you. It's a class that define this this processor. And in that line of code, and if people are not very familiar with, 100% familiar with Jupyter Notebook, you would notice something that is not necessarily a Python script, is this person write file FLOGA processor. That's a trick that we are using here, because that HDF5 processor is something that we're going to reuse in time. And actually what it does is that actually creates a file called FLOGA processor that you will see in your netbook here, FLOGA processor. Because we're going to load that in the other part, this exclusive part, because it's a key element that allows you to read the H5 files and get the access the different satellite images. But let's start running this HDF files. We create a class, it's a processor for this H5 files. And here in particular, I'm importing that things from that file, and I'm reading the dataset path, and I'm reading and process the year 2017 and the event ID 0. So once that might take some time because it's basically go inside the H5 files and look for the event data that we're looking for. In particular, as we can see here, it actually fetched the Sentinel-2 pre-fire, the Sentinel-2 post-fires, which has these shapes, and the label which has the shape. So the shape is the dimension of that tensor. And it has unique labeled values ranging from 0 to 1. So we have some pixels that have been burned and some pixels that have not been burned. Then we are going to use here raster.io to save the information of those satellite images in a TIFF format, in a GeoTIFF format. So this is the defining of the output path. We calculate the metadata, the metadata processed here. We get the data of the Sentinel-2 pre-fire, post-fires, labeled band names. And here I'm just writing these files here for every single band. So if I run that, I basically saved the pre-fire image in the folder content drive my drive CV4EO output part 1, and an image that represents the FLOGA 2017 event 0 with Sentinel-2 pre-fire. Same thing, and that's the first output you can see here in your CV4EO output. It's the Sentinel-2 pre-fire. Then we're going to do the same thing with the post-fires and the label. And the reason why I'm doing that is also to later on have access to it on your own computer. So once you have run the next 3 cells, those actually save also the Sentinel-2 post-fires and the labels that was manually annotated as a TIFF. Okay, so
after running 1.2, I've still got the writing FLOGA processor.py. Can I go on, or do I have to wait until that's finished?
1.2, this one?
Yeah.
I think it should already be on. For me, it has run. So here you can see it actually says green tick. It has run in 0 seconds. So maybe we can have a look at what.
It just says at the bottom. It just says writing FLOGA processor. Yeah.
Ah, yeah, it's already it's written actually. It's not writing. It's written.
Oh, it's done.
What's done? Why notice the green?
Okay. Yeah.
Is done.
Okay. Great. Thank you.
Right. So you can run the next cells.
Right.
Okay. All right. Great. So we have saved those three files. Now the first thing we can do is actually we can open these images in QGIS. So here I have also QGIS. You see my QGIS? No, you cannot. Need to change something here. Stop sharing again. Okay, you can see my screen. So this is my QGIS that one of the only GIS I'm actually a bit familiar with. And what I have as well is that I have Google Drive being synchronized with my computer, so I can find the 3 files that has been generated right now in the TIFF format. If you don't have Google Drive synchronized with your computer, you can go back to the Jupyter notebook that we are working with, and you can click on the file that has been created. Here, this is the label and the pre and post fires, and you can actually download that file. Now, going to QGIS, what we can do with QGIS is adding a layer of a raster layer, which is basically how the GeoTIFF is handled. And I can select my files that I have created. I'm going to add them to here. Perfect. And I can visualize what it looks like. Here, I have, first of all, the pre-fire. This is the visualization. So if I look at the properties, I'm actually showing the RGB, the red-green bands, actually using the band 1, 2, and 3 of Sentinel. Can actually play around with those bands to actually show specific bands in particular that corresponds to the near infrared. You might be more familiar with which band is actually this.
Can you try in the red to put the channel 11?
11.
Then in the green the channel 8,
Okay.
and the blue channel 4 or 5.
Okay. Great.
Yes.
That's basically one of the reasons. And what does that correspond to?
So the band 11, this is the short-wave infrared,
Okay.
which is absorbed by the water. The green outputs the infrared, because the infrared is reflected by the canopy, by the leaves. So if you have a lot of vegetation, it's going to be green.
Okay.
That's what you see there.
Okay.
And GB, the blue, outputs the channel 5, which is the absorption by the chlorophyll. And so basically if you have a lot of chlorophyll, it's going to be low, and you don't see the red, so you will see the green vegetation. And if you have a green scar, then you will see the burn red, reddish color.
Okay, all right. So that's the pre-fire, and I can do this. I can also show the label. The labels looks like this. So if I alternate really quick, this is pre-fire, so we don't see much information about that. I will do the same with the post-fire. We're also going to see the same bandwidth. So 11. Oh, wait, band 11. Just want to make sure I'm doing the right things. So it's 11.8.4. So for the pause, I go to the properties. 11, 8, and 4. So this is the same thing for post-fire. And if I remember, I think we can actually, I actually quite well identify that this is the region of fire here. So if I see that that's the label that's been annotated, and same thing happens here. And if we do before and after, I think we can quite well actually identify some of the regions.
Sorry, there is just a question for you. In the list of bands, we see the bands are listed, and then there is the label of the bands, and there is a like band 11 is called B12, and band 10 is called B11. So
Yeah, there's a shift.
yeah,
Yeah.
no, because there is the band 8A somewhere in between. So I should rely on the left or the right?
The right.
Right. Okay.
Ah, okay.
Right. But,
So it's not yellowish; it's more green then. Because for me, the output is greener.
But B11 and B12 are more or less very one next to the other, so that's
Okay.
The B8, the infrared should be B8,
Okay.
and then B5 should be the red channel, and B4 should be the blue channel in Sentinel.
Okay.
Okay, that's important.
So that's like the first access of the data with QGIS. We have loaded the data on with H5. We have read the images. We have saved them in a GeoTIFF, and we have opened them to a QGIS. It's important. Those steps are important because in the next steps we're actually gonna play more with this type of data. But let's move on. Taking a bit of time, I think we might go a bit faster for the remaining. Here then in the 1.5 we're displaying the data with some Python code. In particular, we're going to use matplotlib. So we're going to read a specific event, and if I run that the 1.5, so here in particular I am reading the near infrared that's basically normalized. Which is the layer 7 or the index 7th in my Sentinel-2 pre-fires, and also the layer 7 was sent to Sentinel-2 post-fire. This is the near infrared, and I've normalized that with the maximum value such that the value are become between 0 and 1. And this is what near infrared look like in the Jupyter notebook. So this is a way to evaluate. Sorry, to plot those details. Then in 1.6, I have a small hand-on exercise for you, which the scope is trying to create an RGB image using ND stack to combine the band red, green, and blue, which corresponds to the band 4, 3, and 2. Correct me if I'm wrong, Pietro.
Yes.
Okay.
That's for the RGB, but yeah, that's the real.
The real red, green, blue, right?
That's
Exactly.
correct.
And if you want to have the near composite, which can be the near red and green would be band 8, 4, and 3. And again, use the function np stack to combine the select bands, and we can actually read them here, and of course normalize them next steps. That's a small exercise. I don't know if you have the time to run that. There's a solution, right? We don't. But I will give you maybe like, don't look at the solutions. Take maybe 5 minutes of your time to look at how that works. Actually, I think for sake of time, because we already took like almost 1 hour for the first part, and I was expecting to do the first 4 parts in 2 hours. Maybe let's move on. So basically, the solution is right below. In order to use NPD stack, actually, you can just take the Sentinel pre-fires, the band 4, because in computer science, the first index is actually indexed by 0. You have to select the bands, the channel number 3, index number 2, and index number 1, which correspond to these bands, red, green, blue, and then normalizing the image with the same function as above can actually create this image. The same thing goes with the near infrared composite. And then you have basically the code like this that you can just click RGB composite or near composite, and you can visualize those different bands. So the RGB looks like this, the labels is always the same, of course, and the near infrared looks like that.
It takes a bit of time to load, but
it takes some time to load, yes. Yeah.
Don't be surprised.
If it takes, it's a bit too slow, it's just like it takes some time to load. Okay? All right. Let's, do you have any questions for that so far? I mean, we have processed the data, so we're good. Let's move on to the second part. If you go to your notebook, you can open the part 2, that includes the solutions as well, where we're going to play with indexes. Here for the indexes, so we have a new environment altogether. So again, you'll have to connect your machine for the part number 2. You still have like, the resources for the FLOGA paper, the code, and the data set. We're still using Google Colab. That's a fresh new Google Colab, so a fresh new Jupyter notebook. So if you go to the part number 2, you'll have again to mount your Google Drive, set some variables, and so on and so forth. Okay. So here in that code, I'm basically reading, connecting my Google Drive.
I don't see part 2.
You don't see part 2. It's in the notebook.
So you have to go back to here.
Okay.
Yeah, and then select the second.
Yeah.
You can double click.
Okay.
And then you need to reconnect on top because it's a new environment. And once it's connected, you can rerun the first initialization of variables. So it's exactly the same as in the first
Okay.
kind of book.
All right, so the first part is actually to mount. Actually, for this, I might actually want to go a bit fast because I'm pretty sure you're actually familiar with those index. We'll actually go through it, and I'm actually going to click on runtime, and I'm actually going to run them all. So running all in the runtime of Jupyter Notebooks basically means it's going to run through all those cells one after the others, so we can actually directly analyze what's the output of what we have here. So in the first cells, I'm mounting Google Drive, I'm defining the path like before, so I'm defining where's my dev kit, where's my dataset, what is the dataset path of the H5 files, same exact one. And then I'm creating an output folder, which is part number 2, which is the second part of what we're actually doing. So creating the directories to have all my outputs that is in Google Drive that you can still see in Drive, My Drive, go to CV for Earth observation output, and that will be stored on the part number 2. I'm installing the libraries, same one, H5 Python, Matplotlib, raster.io, and so on. And now I'm going to play with the spectral indexes. You might be familiar with the NBR, which is the normalized burn ratio that is defined as the near infrared minus the SWIR divided by the near infrared plus the SWIR, and just adding a small epsilon to avoid the division by 0, just in case that sum is actually equal to 0. That formula actually calculates from the near infrared and the SWIR the normalized burn ratio. So here I am actually just loading the FLOGA processor. So that sys is just a trick to have access to the HDF5 processor that we have defined before and we have stored in the file. I am reading the path of my dataset in H5 format. And the SWIR means the shortwave infrared, yes. So from 1,400 nanometers to 3,000 nanometers, or the near infrared from 780 and 1,500. But I'm pretty sure everyone is familiar with that. So I'm reading again the year 2007, the event number 0, calculating the metadata, so I'm basically extracting the Sentinel pre and post fires, labels, and bandwidth. So same thing as before. Now I'm extracting the near infrared and the shortwave infrared, which corresponds to bandwidth of the band number 8 and the band number 12, which corresponds to these indexes in my matrix, my tensor. And I'm calculating that normalized burn ratio with the near infrared and the SWIR. And I'm saving that information again with raster.io in the R2 FLOGA event NBR pre. So again, you can open it with QGIS. So then you can do the same thing with the post fires. It's basically saved in your Google Drive. And you can go to your QGIS now and also open that specific layers. So I'm going to add layers, raster layer. Here I'm selecting the data that comes from part number 2. I've just generated. So I have the NBR post and pre that has been calculated. I'm adding them. And here you are. So the label should look like this. And burn ratios from the extracted values. I might need to select a few properties of what I want to display. I might need to play with like some threshold or what I would actually want to show. I'm not very familiar with that part. But basically this is like the NBR index for the image, pre-fire and post-fire. Not sure if it actually visualized very well, but the scale is a bit then we can do the same thing with the differentiable NBR. So the DNBR, we're basically taking like the NBR pre-fires and post-fires and just do a difference between the two, calculating the DNBR and save that as well. Same thing with oh yeah, I can move to like the next thing. I can have interactive sessions where I can play with that threshold and try to identify a threshold that create a binary mask from that index. And I think playing with the threshold allows you to maybe create like a binary mask.
It just takes a bit of time to.
Takes a bit of time,
Yeah,
right?
so to reload the binary mask. But,
Okay. I don't know what type of threshold you use to have like a low one. Right?
Yeah.
But this is a way for you to play with the indexes and sometimes get like some good files. Is it good or not? It depends. I think this normalizable ratio does not necessarily work in all the cases. Okay.
Might even start.
Okay. All right. Good.
And if you look on the water, there's a whole mess.
Right.
And I know that people are using NDBR to detect water.
Okay. All right. Of course, the water cannot burn.
Well, but the NBR there, it's an index that you can retrieve also vegetation, water content, you can retrieve everything.
Okay.
Now it's an index, as it says, it gives you an idea of something.
Okay.
And maybe not optimized for burnt area.
Okay, I see. All right. There's another index called BAIS, so burned area from Sentinel 2. I forgot what it stands for, BAIS. I forgot what it means exactly. But the calculation of the BAIS actually used the band 4, 6, 7, 8A, and 12, and it's a very complicated formulation that might or might not work. You might know if it's better than the NBR or not. Again, we say that in the TIFF. We also have the NBR plus, and we can visualize them all. So once you have run everything, basically you should have in your Google Drive the BAS2 TIFF, DNBR, NBR plus, NBR post-fired, NBR pre-fire, and you can open them in your QGIS and play around with these indexes. So that basically is one way of processing the data. It's not optimal, but it's a way to process your data. All good? Any questions online? Any questions here? Oh my, was I a bit too fast for this one?
maybe we can show again the table that was present in the FLOGA paper,
right?
To just see where we are in the performance so far.
That's a really good point. So yesterday I showed you that slide. That slide is basically coming from the dataset from the paper FLOGA. So from that specific dataset, they were trying to compare the performance of the new model called BAM-CD. And again, I think I told you to focus on the F1 score for the burnt area. You can really see like that the DNBR actually achieve a F1 of 45. That's relatively low when you see that machine learning algorithms that are random forest that we're going to tackle now can reach 67. Deep learning approaches are a bit better, and BAM-CD can reach 81 in that metric. It's a metric that ranges from 0 to 100. So you can see that the performances of the indexes, and the higher the better, and the F1 and the indexes are not as good as machine learning and deep learning approaches. Yeah, basically that's any questions? All right, so if we're done with the part number 2, we're going to open part number 3. In the part number 3, we are training, we're going to try and train a machine learning algorithm to identify this burn ratio. And here we're going to see that it's starting to be a bit better, and we'll show you how. So again, we are in a new Jupyter notebook, so you have to again connect the runtime and mount your Google Drive, install the library. Again, I'm going to do runtime run all, just because it will leave the time for me to actually go over the Jupyter notebook and explain you what every single function actually does. So you have to accept again the access to Google Drive, to Google Colab, so you can read the data set and extract some outputs. Are there any questions so far? Is it like too fast? I'm happy to have any feedback on that. So far, so good. All right. So in that first line of code, I'm mounting Google Drive. I'm installing the Python libraries again, defining the path here, defining a path to have the access to the HDF5 processor class to manipulate the FLOGA dataset. And in that specific part now, we're going to actually use machine learning to train a random forest classifier. The random forest classifier is an example of that Anthony actually showed yesterday when he was showing like a binary tree could actually be trained. That's actually a random forest classifier. We're going to see the advantage of like how robust it is against noise, it's less sensitive to overfitting, and efficient with actually small data sets. So here, here we are still actually using only a single image right now, and we're going to actually train a random forest classifier on only a single image, and hopefully going to generalize well to other images. So some technical details here. I have a class for training a random forest, and in particular, I'm using a library called scikit-learn. I don't know if you're familiar with scikit-learn. It's a really good machine learning library that can give you a lot of classifiers without having to write yourself to algorithms. In particular, we're going to use the class random forest classifier. We're going to use the train test, the function train test split, because as I told you originally, we want to train on some data and test on a different data. And we're going to use some metrics as the accuracy and the confusion matrix to evaluate how good we are in this task. The training code here is first taking your so given a value x and y. So you remember in that formalization that we presented yesterday, x is your input and y is the output. And in that particular, this is not y hat, it's not the prediction, it's actually the ground truth, the expected out, the labels. So given an x and a y, I'm creating a test size of 30%, and I'm just like putting a random seed at 42 to avoid like any, you just like to enforce reproducibility, 100% reproducibility of what's happening. That creates for me the x value for training, the label value for training, and the input value for testing, and the output value for testing, label value. I'm creating the random forest classifiers with a 100 estimator, and I'm going to use the function fit for machine learning that's basically going to fit my random forest classifiers on the X train and the Y train. And then I'm going to predict on the test set to have my Y predictions. Then I'm going to estimate the accuracy score of Y test and with respect to the Y prediction. So this is the ground truth, this is the predictions. I'm going to get an accuracy, and I'm doing the same thing with the confusion matrix. And then I'm going to plot those informations. So this is like what that class is actually doing. And then for the predictions, given the models and an image, for instance, the near red, green dimension, we actually want to create predictions of that models and return the prediction itself. So here's like some information about how the random forest classifier work. In particular, here we are using a random forest with 100 trees. This is the number of estimators that are combined together to get like the best one. I won't go into the details of how the random forest classifier works because it's not the scope of that. But the most important part is that we have a training set, we have a test set in that specific case. We don't have any validations in machine learning, so we only use training and test. Because there is no hyperparameters to actually fine-tune like in the deep learning.
You can, but it's not. Yeah, it's not as important.
It's not as important as in deep learning. Right? And for reproducibility, we're just putting the random state or specific values to have 100% reproducibility. So again, I'm using my FLOGA processors to basically extract one image. I have my images extracted here. These are the same exact representation. And I'm creating here as an input a three-channel image that is composed of the near-infrared, the red, and the green. But here we can actually play with any type of band, and we can actually change that to another type of band to actually train machine learning algorithms to output the labels that we're actually training on. It corresponds to those indexes, 7, 3, and 2. And the shape of that object is actually three-dimensional cube. I'm also saved that near red-green infrared, near red-green composite image into a diff, so we can later on read that. You can see it in your drive. my drive output part 3, one of these files are actually the near red-green composite TIFF image. So I can display it here. Actually, it looks like this. So here I'm using matplotlib to show the NRG composite, near red-green composite. I'm also playing with the label. So this is what the near red-green composite image look like, and this is the true label of burnt versus unburnt look like. In the 3.3, I'm preparing the data for the classification. So what I'm going to do with this random forest is basically take every single pixels and classify them, whether it is burnt or unburnt. So in this specific aspect, I'm not actually using any convolution neural network or any neural network itself. So I'm just going to flatten the whole pixels such that it has a dimension of all the pixels. Every single pixel now is actually an input, and I want to know for a given value of near red-green, whether it is burned or not burned. So preparing the data for classifications, given the labels and the input data, is basically to flatten and to reshape that. So basically, I want that to be one-dimensional arrays. Actually, a two-dimensional in that case, because we have the 3 channels and the vectors of all the pixels that are basically flattened. And the same thing actually happened with the label, and I'm creating that in the binary. So 0 mean unburned and 1 mean burnt. I'm preparing my data with my NRG composite and the labels, and I'm showing what the features I'm actually taking, or the inputs of my classifier look like. I have in particular 3 million pixels of 3 components, near infrared, red, green, and labels that corresponds to all of each of these pixels. Here, what I'm doing is training that random forest by just running the function I called before, called train random forest, with my x and my y that I've prepared here. And you can see that's trained. The training can take, actually it took 4 minutes, you can see, because he is actually doing all the optimizations in a hidden way. So it takes some time. So if you haven't run that at the very beginning with runtime run all, that step might take some time.
Maybe if you want to go back to the slide, just to show a bit what is happening here. So the slide on random forest, which was at the very beginning, yesterday. Yeah.
That's the random forest.
So basically what we are doing here is exactly the same as what is on the bottom of the slide, except that here, instead of having just x1 and x2 values, we have x1, x2, and x3, which correspond to the near infrared, red and green values. And what we are doing with this random forest is building a bunch of trees, like the one on the right, automatically to find a decision boundary between x1, x2, and x3 that separates the burnt area from the unburned area. And we are using the labels for that. So here, for instance, the red dots could represent the burnt area, and the green dots the unburned area. It is exactly the same as this, except that instead of having one single tree, we have a lot of them that are going to be built. And then the decision of each of those trees will be combined through some kind of consensus mechanism.
Perfect, thank you. So that's what happened here when we actually trained. We actually estimated all these different trees and we combined them together. And we have, in the training, we actually show like the accuracy that corresponds to 99.92, which is extremely high, as you can identify. And the confusion matrix looks like this. And here's something that I would like to basically pinpoint. Like, despite the fact that the classifiers actually tells you 99.92% is actually correct, the accuracy doesn't provide you a full understanding of the model performances. Why is that? Because you are in a case where the data is actually extremely imbalanced, which means that actually among the pixel that you had, you were basically almost 1 million of those pixels were properly classified as negatives. There is no burn fires. So those are called the true negatives. Those are the correct predictions for the unburned class. The false positive, which is the unburned pixels that are always like incorrectly classed as burned. And here what you can see is that actually 199 pixels have been classified as burned, but there are actually no burn area at all. The false negatives, those are the number of pixels that were incorrectly classed as not burned. So this is burn pixel, burn area that was identified as, oh no, there is no burn area here. And then the true positive is actually the correct predictions that you had, which are only 443 pixels. So because this is extremely imbalanced data sets, like most of the pixels are actually black in the labels that you can see here, my classifier, if it considered everything as unburned, would actually have an accuracy that is close to 99%, because it's an extremely imbalanced case, right? So in that specific case, that specific metric of accuracy is actually not a good metric, which is one of the reasons why in the table they were actually relying on the F1 score. So let's also look at what a result look like actually. So here I'm saving the models in a job lib format, and I'm making some prediction. The predictions is saved in a file called burnprediction.tif, and we can look at it in QGIS, and it's actually not that bad. In that specific case, I will go to QGIS, layer, add a layer, raster layer. I'm going to take my image that I've just generated right now. This one. And this is what my burn prediction looked like, and this is what my label looked like. So actually it's not that bad when you look at it. It's still like performing like quite well. So this is my image. If I put the labels, you remember that basically this was fire. I think some area here was actually burn area. The label looks like this. And if I switch with my predictions, this is what my prediction does. It's not that bad. I'm able actually somehow to localize most of the pixels because I'm using some channels that are quite informative. But as you can see, some of the pixels are not fully classified there. And they have like some random areas here where you actually thought that there was like some fire.
Yeah, and this is also due to the fact that here we are classifying pixel by pixel without taking into account the spatial correlation between the different pixels, right? So if you remember, when we were doing deep learning and convolution neural networks, one of the advantages was that it was leveraging this spatial correlation. And here, since it is not, it's actually making the prediction of one pixel without considering any of the others. And so if for some reason one of the band is higher in that region, whether it is noise or anything else, it cannot smooth the entire prediction.
Right, exactly. So those are like the burn predictions with the labels, and basically in the prediction, I don't know if you can see it, but here you have a few points that actually have been classified as fire, as burn area, which is not the case. There is also a region here with a few dots, that a few pixels has been classified. So it makes some mistakes. So despite the 99.92% accuracy, when you look at like the confusion matrix of what has been properly classified to good binary, good values, actually it's not necessarily that performant. Here there is an end-zone exercise that maybe we're going to go a bit quick on that, where the scope would be trying to play with like basically complete the different functions here that allow you to estimate the predictions on unknown images. Here we actually showed and trained and evaluate on image number 1, the event number 0. But what happens if we actually input a new event? Does it generalize well? That's a question that arise. Like if I've trained on one area, does it actually generalize to another area? And with that exercise, you can actually create the event ID for the event ID number 2. You can create the composite images, predict the burn area, compare that with the ground truth, and provide that the performance of accuracy and confusion matrix. And
I think we have time to.
we have time to spend to
Right.
work on that.
We have up until 10:45 to the 4th.
I think 10:30 would be better.
10:30 would be
Yeah,
better.
we have some of the performances to actually.
Okay.
We're not exactly following that.
Okay.
So maybe we go directly to the solutions. Basically, you can load the model, the event, load the event ID number 2, create the bandwidth, predict some burn area, create the TIFF area of the predictions, saving them, and analyzing the confusion matrix. And if I run that part, basically load the trained model, see the solutions, loading and processing the image. Notice something quite interesting. Loading the shapes, loading the images, making the prediction of the new image. Right. And here it tells me that on that new image, I have an accuracy of 99.51. So people might believe like, wow, that's amazing. 99.51% is actually correctly classified on that new image. I can also look, can actually look also at that image, and I will load what I have generated. If I go to add layer, raster layer, and I will load that exact for event number 2 here of the burn predictions. I add that layer, I close that layer, and this is what I predicted as fire. I don't have the image of the RGB stored or not, like the Sentinel, but this is where it believes fires are in that specific image. That is actually completely random. And you can see this is actually salt and pepper. It's just like some random noise. So actually, that specific models, although it tells you that 99.5% of the pixels are actually properly classified, it basically has put like a lot of random, they have learned some random things that does not correspond to the labels. I will actually try to do, maybe I should just like print what the label look like.
We can have a look at the confusion matrix still.
The confusion matrix actually tells you the bigger picture. The confusion matrix is basically in the diagonal, you have on the top left the number of pixels that are properly classified as background. And in the bottom right, so basically the second row and the second column correspond to the second class, which is the burn pixels. And here I only have 3 pixels that are properly classified as fire. So despite the fact that the accuracy is 99.5%, the accuracy is a very bad way of estimating the performances. In fact, we have confusions between burn and unburn. I think this 15,000 pixels are basically pixels that are classified as burned area that do not correspond to burned area. And the 562 pixels that are in the bottom left are the number of pixels that should have been classified as burned area and that has been classified as unburned area. So it's really bad, but the confusion matrix tells you more than just the accuracy. And it's like basically one of the key points I want to show here is that having a good metric for your performances, something that makes sense for you, is extremely important. Sometimes some people will come to you and tell you, look, I'm going to have an accuracy of 99% to detect fires. That maybe means that actually they can just like detect background. So having a full understanding of those metrics is extremely important for you to understand whether someone is actually telling you, depicting the real performance of this algorithm.
And Sylvia, if one day you have the image, it looks like you are detecting the reverse.
That might be the case, yeah. I'm sorry, I don't have that one. I might be able to run real quick that guy. In the first one, I have I think it's I will take number 2. Number 2. Might be able to go back to the part 1 and show you what it looks like. Great, it has been stored, so if I go to my QGIS, I have that image somewhere, I will... Here, add the layer, add the master layer. I'm going to my part 9. I'm trying to figure out where that has been stored. Still don't have the images. Here. Okay, anyway, sorry about that. It's actually here. Post. Download. Right here, so. Okay, that's the RGB image actually that it comes from. Is it the RGB? No, it's not the RGB, sorry, it's the properties. Which bench was saying, like 11?
8, 4, 5.
So mine would be this one. Okay, anyway, maybe not this one in particular, but this is basically what the ground truths look like, and this is the predictions that happens, which is a bit weird.
Okay.
So there's no, it is. All right. So that's actually the introduction of the part 4. That is basically about metrics. Metrics is extremely important to consider, and the accuracy is not a good way to actually estimate some performances when you have extremely imbalanced data. So in the part number 4, connect that. And I can only have like a few sessions. Oh, it's not yet. Good point. Yeah. So in the fourth part, I will run all 2. Here I'm going to actually spend some time in just like performance analysis before we have a small break and before we actually go to the deep learning part of how to train deep learning. So here I'm connecting myself to Drive again. Okay. Here I'm evaluating like the spectral indices and the machine learning predictions. I'm going to look at the DNR and the VAIS2 and the random forest classifier that I've just shown. So I'm looking at those results and I'm loading the data. Here I have a small exercise for you where this piece of code actually reads the specific file that can be labels, DNBR, BIS2, or the burn ratios, and you can actually look what it looks like. And the burn ratio that we just have run looks like actually running. 4.1, I'm actually loading that things. This is like what the burn prediction looked like for my image that I had before. And I have the same one for the labels, the DNBR, and the BIS. Here I have a small exercise for you, which is to create a function that returns the binary mask from the path of the TIFF. Because the DNBR and the BIS actually are ranging from, I think, -1 to 1 or 0 to 1, I forgot exactly. And the burn area is also not necessarily like a fully 0 or 1. Solution is just below. Actually, maybe we can fast on that. This is how it looks like. We can read the data that we have stored before from part 1, 2, and 3. And here we're actually plotting them. And this is what the three value actually look like with the different threshold that I've chosen. As you can see, the random forest is actually relatively close to the ground truth. The BIS and the DNBR actually are highly saturating because of the water. Evaluating is extremely important, and here I'm using scikit-learn, again, the metrics to actually estimate the accuracy and the confusion matrix. And here, if I compare the performances of DNBR, BIS, and random forest, I actually have a value of, for DNBR, of an accuracy of 81%, for the BIS of 36%, and the accuracy of 99.97% for the random forest. And here you can see the different confusion matrices that you have access to, and you can see that the BIS, the DNBR are actually completely wrong. In the confusion matrix, basically you want high values in the diagonal of that matrix and have very low values on the side. So here's quite high for the random forest, quite high, but this is basically true positive, false positive or false negative. So we can observe now how the performance actually look like. One of the exercises I would invite you to do is, without looking at the results here so far, the answer is actually to create new metrics. New metrics and how to write your own confusion metrics, where you actually read the value of the two images, the ground truth and the predictions that I have loaded, and extract the accuracy, the balance accuracy, and the F1 score of that of those results. And you need like a few bit of time for everyone to write your own confusion matrix in this code. Makes sense. It's a small exercise for everyone. How to, given the value of Y and DNBR and Y true, these are the images of the predictions of the DNBR, the prediction of the BIS, the prediction of the random forest, with respect to the true value of what I'm expecting. Let's define your own confusion matrix, like write the code that actually help you identify what is a true positive, what's a true negative, what's a false positive, what's a false negative, and extract out of that the balanced accuracy and the F1 score.
So I'm not very familiar with Google Drive. Can you show me where these files are, the output files are?
Sure. I can show it to you here. So if you go to Google Drive, you should have something called My Drive. And this is like all the files that you have on Google Drives. And I have a lot of them. There is like a shortcut for computer vision for Earth observation DevKit, which is all the data that I've shared with you that you have reading access to. And then there is another one called Output that outputs all the files.
Here. There's nothing in there.
Did you run the notebook?
Yeah.
Can we try it again?
Sure. Everything was wrong there. It's just that I don't see the output file, so they're folder.
Are you supposed to have something in part 4?
Not yet.
Not yet.
So I don't see the output folder.
Otherwise, number 3, yeah.
Ah,
So you
okay.
have everything saved.
Yes.
It's just that in part 4 we have not reached we are saving it. Okay.
All right. Thanks.
Part 1, 2, 3, you actually extract the labels, the output of the indexes. Part 3 is the output of the random forest.
Yeah.
Okay. Compare the different results together.
Good, good.
It'll take some time so to answer some questions that you might have about that first part. So if we summarize a bit what we did so far, we processed the FLOGA datasets, we extracted if images and the labels, what it looks like. We extracted indexes, we extracted segmentation of images with a random forest as well, and now we actually evaluated the performances. After that, we're going to deep dive into how a deep learning model looks like and how to train that after the break. So the take-home message is mostly indexes are not necessarily that robust usually. You can train machine learning with random forest to have a better way to extract some specific outputs, and you can also have different inputs, right? Right now we only use the near-infrared, the red and the green, I think, indexes. We can actually use different value. Maybe you combine that with the SWIR, or you combine that with other bandwidth that are available on Sentinel 2 to get like even better performances. So we also play with these machine learning algorithms to derive new functionalities, new combinations of those different inputs to reach the better outputs. And everything is learned in an end-to-end fashion, so we can actually learn something, a model that would work on any type of input. And here in the fourth part, we are actually trying to identify what is the best metric that we're looking for with that exercise. I'll still give you maybe a few minutes to try to write your own confusion matrix, extract the balanced accuracy and the F1 score, and then I can show you maybe like some answer of that and show you how the balanced accuracy, maybe an F1 score are better way to estimate the performances of your algorithms.
Right, again, for the Google Drive, they've got the TIFFs now, but I don't see how I can take them into QGIS.
Okay. Do you have the Google Drive installed, the Google Drive clients installed already in your computer, or you can just like click right click and click download?
Okay, so I download it. Okay,
Right.
fine.
So you download button, just like download it locally.
Okay.
If you have the Google Drive clients, basically it automatically synchronizes on your laptop all the data you have recorded in Google Drive, so you can directly find it on your laptop.
Okay. Thanks.
Okay, so let's look at the results of this exercise. I hope some of you actually managed to write some of these functions. The confusion matrix images, basically given the ground truths and the predictions, is basically given by that. So the confusion matrix is basically the matrix that we showed above. This basically tells you like how many true positive and false positive and everything you actually have, and is defined by that line of code. This is the true positive. So the sum of all the elements on the ground truths and the predictions that are both to 1, that means it's a true positive, which means like 1 is positive and the true is actually you are correctly predicted that as a positive as well.
And this is the fire part.
And this is for the fire part, yes. Yeah, I forgot to mention that. This is for the fire part. The true negative is whatever is actually both 0 and 0. So if you have a 0 and a 0, so the expected output is 0 and you actually predicted 0, that's a false, a true negative. Negative means it should be 0. It's truly a negative, which means you have correctly estimated that as a negative to 0. A false positive is whenever your ground truth is actually 0, and the predictions is actually set that to 1. So you have that. If you have that case, the number of pixels that are set to 1 by your predictions and are actually equal to 0 in your ground truth, this is the false positive. And the last one are the false negative is the opposite. Whatever should have been set to 0 and that we actually have predicted as 1. And basically the confusion matrix looks like this. Now, the confusion matrix is extremely useful because it tells you a lot of information about the different results and actually help you identify the balanced accuracy. The balanced accuracy is kind of an accuracy that is balance between that take into consideration the imbalance between the classes. And to give you some details, but this is like the estimation of how you define the balanced accuracy, defined as the sensitivity and the specificity. And now when I estimate actually the balanced accuracy of the DNBR and the BAIS, and the one from the random forest, I realize that actually the balanced accuracy of the two first actually around 50%. And what does it mean actually having accuracy, a balanced accuracy of 50%? Because we are actually in a binary classifier. 50% is not better than random. So we're actually not having more than random classifiers actually for those two indexes. So not very suitable for that specific case. But the balanced accuracy for the random forest is actually to 95.99%, which is a bit more in line with the imbalance between the two. So originally we had 99 point something for the accuracy. When you take the imbalance between the two classes, we're actually more at the 95.99%.
Just specifying that here we are testing on the training set, which is why the performance is so high compared to.
Yeah, I forgot to mention that. Sorry.
Here we're just testing on the training set.
Right, right.
It's not to be compared when testing on the testing set.
Right. It does not generalize well yet. So this is how we're going to go with for deep learning for both generalization. And the F1 score is basically also defined by the precision, the recall, and that function in particular for precision and recall, which is basically a function of the true positive, the false positive, and the false negative from the confusion matrix. And if we look at the F1 score, which is basically, it estimates more like the overlap of the regions somehow. And if there is no overlap at all between those regions, it's actually close to 0. And when there is a very high overlap between the two regions, it's actually close to 1. And in that specific case, the NBR and the BIS are actually close to 0, while the random forest is actually close to 81%. So in conclusion here, we have compared the performances of the spectral indices in the machine learning in the burn area detections. And we saw how the metric that we actually use to evaluate the performances is extremely important. And in fact, in our labs, and especially Anthony's lab, there have been a lot of research on how to evaluate properly those algorithms, those performances. And Anthony has a small presentation of his latest work on how to evaluate properly performances.
Thank you, Silvio. Perfect. Yeah. So here I'll share with you a bit of our latest work. So this is a trilogy, actually, so 3 papers that are going to be released within the next 2 weeks, so before December 9. So here you are actually the first to see that presentation and that work outside of our laboratory. And I'm very happy to present this work here, but I will ask you not to share details of what you will see and slides before December 9, after that's okay, but just before the paper are released. And I will follow up with Pietro to give you access to those papers as well as soon as they are released. But basically what are we trying to do here is to understand from a theoretical perspective the theory behind performance-based ranking. What does this mean? This means that we have a bunch of entities that we want to rank between each other. And these entities, they can be classifiers, segmenters, object detectors, whatever. So in the first paper here, we're really laying the theoretical basis, which are based on a lot of mathematics, an axiomatic proposition that we do in the paper, and then we derive some theorems and some ranking scores that you can use to analyze the performance of classifiers and to rank them, so know which one is better than the other. And so I'll just give you a bit of motivation first and why we needed this theoretical foundation for performance-based ranking. You may have asked yourself questions like this, like which score, or it is called sometimes metric, should I use to analyze the performance of classifiers? So like here, the indexes, the random forest, the deep learning algorithms. What score do I use? Do I use the accuracy? Do I use the balanced accuracy? Do I use the F1 score? And it's a bit blurry in the literature. Usually you follow whatever was done before and you just check if your method is better in one or the other metric. But what does it mean actually? Then when you design a new classifier, you want to know if it outperforms existing one. Is it the new state of the art that you have proposed here in your new paper? And finally, how do you decide which score to use when you want to rank? So if you have to select here, for instance, between like the indexes, the random forest, the BAM-CD deep learning model for your own on-mapping applications, which score do you use for ranking those classifiers? And these are all the questions we try to answer here. So what was done commonly in the literature is that typically you use one single score or a few scores and you look at them, and you have, for instance, the accuracy, the precision, the recall, the balanced accuracy, or the F1 score, like we've seen in this notebook given by Silvio. And when you rank all the methods based on one score, you may have something that looks like this in terms of ranking. So the green method comes first and the red method comes last. And then if you change the metric, it's actually the opposite. Maybe the red method comes first and the green method arrives last. So it's very difficult to make a decision based on those scores. And this is because these scores only reflect a part of the performance. And actually, even if you take the accuracy, the precision, the recall, and so on, you will not have a full global understanding of what the actual performance of an algorithm is. And also what happens when the prior are imbalanced. So like in this case, the parent area only represents 0.1% of the background of the whole image. And so the background takes a lot of place in there. So how do you handle this stuff? Now, you may have heard also of commonly used evaluation spaces, such as the ROC space. That is basically plotting two scores together. So the true positive rate right here on the y-axis and the false positive rate on the x-axis. And so the objective is to be as close as possible to the top corner right there. But if you look here, I've plotted some methods that have been proposed in the literature for semantic segmentation. And it's actually very difficult to know which method is better than the other. So for instance, you can say that definitely those methods should be better than those, right? But how about between the two ones that are here and there? Which one is better? Very difficult to make a clear statement. And it's even harder to make a full ranking of all the different methods. Now you may have also seen these precision recall curves that plot so the precision. As a reminder, the precision is so the true positive divided by the true positive plus the false positive, which is basically among everything that I predicted, how many of those predictions are actually good predictions. And the recall, that is among all the positives in my dataset, how many did I find? So the true positive divided by the true positive plus the false negative. And here I'm plotting two classifiers, so classifier A and classifier B, and the curve is constructed by changing the threshold on the decision of that classifier. So this would be changing the threshold on the index, the normalized win ratio, or the BAIS, for instance. And actually, when you're looking at this, you're not looking at one classifier, but that family of classifiers, right? That depends on the threshold. So as I'm going around that curve, this is a family of classifiers. And it's actually very difficult to compare A and B. Which one do I use, right? And so in our papers, like I said, in the first paper, we laid the foundation of performance-based ranking, and we propose an axiomatic definition of this performance-based ranking. In the second paper, we particularize it to the two-class classification case. That can be also two-class segmentation, of course. It extends naturally to the two. And we propose a new tool called the tile that I will present right after. That is actually a way to represent all possible scores, ranking scores, that we defined in the first paper in a 2D map, and that can be used to analyze performance of classifiers. And in the last paper, we provide a user guide. So depending on what you need to do, whether it is to, you propose a new method and you want to see how well it performs in different scenarios, if you want to benchmark different methods or rank them, or if you want to select a method based on what is available already. So the first paper is very mathematical, so I've tuned down to really give you the key messages in there. But if you want the full detail on this, you read the first paper, very mathematical, but it is a very generic representation of performance-based ranking. In the second one, it's still very theoretical, but it is applied to two-class classification, and we provide a lot of links between what we propose, so the tile, and the rock space and other metrics that are used commonly. And if you just want to use the tile, go to the third paper. It is a guide written in very simple terms. So a question, what do I want to do? How do you do it? Very simple. And so those papers I will transmit to Pietro that can then share them with you. So first of all, what are the three axioms? So I've tried to take the mathematics and understand it with simple sentences that represent the general ideas. And so these are our own proposition for what we think is important for performance-based ranking. So in the first axiom, we say that adding a new method to an existing rank should not change the relative rank of existing methods. So it means that if I propose a new method, the relative rank between all previously existing methods should not change, which makes sense, right? In the second axiom, we say that the ranking should reflect the task. So we should be able to say which cases are satisfactory and which cases are not. So for instance, the true positive and the true negative are satisfactory, and the false positive and false negatives, you don't want to have them. So also makes a lot of sense. And the third one is maybe the trickiest, but it's that a blind combination of methods cannot lead to a better performance than the best method. So if I go back to the example of the rock space right there on the left, this means that I cannot blindly combine the classifiers that are existing here to go below that supremum curve. So I cannot get a better classifier by simply blindly combining the classifiers, the existing classifiers. So once we agreed on those axioms, we tried to find if there were solutions for finding ranking scores that satisfy those axioms. And actually there is, and there is a whole family that can be parameterized in this way, so an infinite family. So here I'm not going into too much of the mathematical notation, but just know that basically what we are doing is that we are summing some important scores that we decide. So we say what is important to us. Is it to have a lot of true positive, a lot of true negatives? Is it to have a lot of false positive or a lot of false negatives? Then we have some satisfaction. So like I said in the second axiom, we have to say whether we like true positive or we don't like false positives, for instance. And then we have the probability of the event, which is like the number in my confusion matrix. So the number of true positives, the number of false positives. And now if we specify this if we particularize this for the two-class classification, what do we have? Well, we have 4 types of events: true positive, true negative, false positive, and false negatives, right? We want a satisfaction of 1 for the true positive and true negative, and 0 for the false positive and false negative. And so the formula actually becomes something like this. So this means that I can define ranking scores based on some importance that I give to the true negative, to the true positive, to the false positive, and to the false negatives. That will be ranking scores that satisfy our axioms. So that can be used to rank classifiers. And what we did is to parameterize this importance according to 2 parameters. So the first one, A, is going from the true negatives to the true positives. And A ranges from 0 to 1. So if it is 0, it means that I give full importance to the true negative. If it is 1, it means that I give full importance to the true positives. The second one is B, that is a trade-off between the false positives and the false negatives. And it's also between 0 and 1. And so this means that if it is close to 0, I give full importance to the false positives and no importance at all to the false negatives. Now what we can do is, since we have this formula and we can and we have 2 parameters, we can actually display that on a 2D map that is parameterized by A and B. And this is what we're doing here, and we call the tile. So when you have the tile here, it's empty at the moment, and I'm going to build a few understandings on it. When it is empty like that, when you are in this corner right there, it means that you're giving full yeah, you can see my mouth now, that I give full importance to the true negative and false positive, but none to the true positive or the false negative. And so what can I put on my map? Well, actually, I can put some scores that you already know. So for instance, in the middle of the map, what do I have? I have the accuracy. Why is that? If I go back to this formula right there, if I put 0.5 for all the importances, I can just remove them from everything. And so I'm left with true positive plus true negative divided by the sum of all events, which is the definition of the accuracy. So in my map, I know that in the middle, I have something that represents the accuracy. And actually, I can put a lot of scores that you already know. So for instance, in the top right corner, you have the true positive rate, which is the recall. So I give full importance to the true positive and to the false negative. So like I said, true positive divided by true positive plus false negative, that's the recall. In the bottom corner, I have the PPV, which is okay. So this positive predictive value is actually the precision. So I'm going between no problem. So I have the precision right there. I also have some true negative rate, negative predictive value, F1 score that is here in the border, and the balance accuracy that actually moves around depending on the prior on this diagonal right there. So this means that in one single look, I will have access to all the existing scores that you usually use, plus all the extras that are in between all of those, and that represent really the full scale of the importance that you give to true negative to true positive and false positive to false negative. So you can really have a look in one. Now I can also link that to the rock space. So if I take, for instance, the ISO performance values, so here in light blue over the gradient, you have all the performance that are the same for here the recall on the rock space. And you can see that optimizing with one score will lead to very different stuff in the rock space, so very different region, depending on the score that you use. So this is one of the advantage of the tile, is that it represents all of these rock spaces in just one look. So now I'm going to go a bit into the different scenarios and what kind of values we can map onto this tile, because we can actually map different stuff. So in the first scenario, let's say that you are a theoretical analyst and you are interested just in understanding the relationship between different scores. So for instance, I want to know how much my ranking, if I rank method based on the accuracy, will be linked to if I rank it on the F1 score. And for this, we can use the correlation tile, which basically means that we can correlate any score with all of the scores represented on the tile in terms of ranking. If the correlation is high, it means that if I rank it based on the score that I'm comparing it to, so for instance here the macro IOU that is used a lot in segmentation, I can see on the tile what are the other scores that will lead to a similar ranking and what are the scores that will lead to a very different type of ranking. So here, what is interesting is that the macro IOU does not respect our axioms, for instance. So this is a score that should not be able to be represented on our tile, but we can correlate it with scores that respect the axiom and that respect all the nice properties that we developed in the first paper by choosing one of the scores that best represents this macro IOU score. This is also very interesting if you want to select a few scores, because if I select, for instance, the macro IOU and the F1 score that is around there, I will have something that is very similar. So I will not have that much contrast to compare the methods. However, if I choose the score here at the bottom, it means that I will have two very distinct view on the performance of classifiers. In the second scenario, let's say you develop a new method and you want to know what are the performance of that method across the whole range of ranking scores. For this, I can use the value tile, which basically maps on this tile all the scores that are computed with the ranking scores. So for instance, in the middle, I will find the value of the accuracy for my method. On this point right there, I will find the F1 score, the recall, the precision, and so on. So this in one look shows me in which parts of the evaluation space my method performs good or performs bad, which is very much more informative than just using a few scores. Now in the third scenario, you want to benchmark methods, so you want to know the ranking between what are the rank of the different methods across the tile. Well, you can use the ranking tile, so instead of placing the value, you can place the rank of the method across a whole bunch of methods on the ranking tile. So for instance, here I'm showing a few semantic segmentation methods. So here you will recognize DeepLab D3 that we're going to use later after. And here I'm comparing 74 semantic segmentation methods. And so we can see that, for instance, ISANET is ranked #1 only in this region. So this means that if the ranking was done based on the precision, ISANET would be first, but actually if it was done on the recall, it would be last, right? So this shows in one look where the method is the best or the worst, for instance. And now in the final scenario, so let's say that you need to make a decision between different methods. Which one do I use? Well, there you can use what we call the entity tile, that instead of showing the rank of the method, we show who's first in which part of the tile. So here we can see that the first method, the first place is shared between 4 methods, so mass2former, SETR, DeepLab V3 in a very small region, and ISANET. And so how do you choose a method based on that? Well, we develop 3 different scenarios, whether you know the importance that you have to give to the true positive and the false positive in your application. So if you know that, it's straightforward. You can directly pinpoint one point on the tile and choose the method that is shown there. We also explain how to do that if you have a typical score that doesn't go inside the tile. So by using a combination of the correlation tile and this entity tile. And finally, if you don't know at all, we also provide some mean ranking across the whole tile to know which one performs good across a wide variety of scenarios. And so, yeah, as a conclusion, what we present in this trilogy of paper is a new tool that aims to replace the common metrics, the use of common metrics that are used, such as the accuracy, the F1 score, and so on, in considering actually an infinity of ranking scores rather than just specific. So it's really like a generalization of what is done before. And through the different scenarios that you can find in our guide, you will actually see how to effectively interpret classifiers and rankings. And so coming with these 3 papers, what we are releasing as well is going to be so a notebook and for you to get experience with the tile, but also some Python code that actually you just input the different confusion matrices of the different methods, and it will generate for you a whole report with all the different tiles that I showed you, and that can be used for decision making or for you to evaluate classifiers and so on. So yeah, hopefully this will be a useful tool for everyone, and I'm happy that I was able to present, like I compiled the slide for you today, and you are the first to know that, so that I'd be happy to have your feedback during the break.
Thanks.
That's pretty good. And so if we can use it, as things change a lot of estimation that we do and how we present the accuracy of stuff. It's pretty interesting. So yeah, super. We will be happy to use that. Okay.
Fantastic. I will share with you everything.
Maybe I have a question.
Yes.
Do you have a scenario for Penny?
Penny?
Penny.
No. Fortunately, we only use the scientist characters in the Big Bang Theory as illustration. So Sheldon, Bernadette, Leonard, and Howard. Yeah. No Raj.
Thanks.
Super.
Thank you.
Yeah. So it's really it's a really practical case. So if you have like some specific on these scenarios, you can actually use this tool to decide how to proceed. So if you're a developer, if you are like someone benchmarking, you can actually have tools now to identify which method is the best, which is a bit better than just like one score. Like the accuracy that can have some issues in balanced cases, balancing accuracy that also have like some other issues that I think is detailed in one of your paper. The F1 score as well, the IOU, the micro IOU. There's a lot of metrics, but it's really hard for us actually to understand which method is the same with a single one. But that tile is somehow summarizing all those evaluations.
And just, it's not one thing that we propose out of the blue. It's really like anchored in deep mathematics. It's exact work. It's not like we propose something that mathematically proven. Based on those axioms, this is what we can do.
I think that's the time for a small break, right? It's been almost like 2 hours that we have had our brains and our hands on into some very deep math and some quite advanced coding. So I think it's time for a break.
Absolutely. And the agenda somewhere. Maybe we can reconvene at is it 11? Okay, so for people online, we will have the coffee break and we will reconvene at 11 sharp. Thank you.